hi everyone again. My name is Leonela, and today our community, Tech Internals community, hosts this meetup. So basically, I will give you just a short presentation on our community, but then of course I will pass it to our beautiful speakers, Jérôme and Pavel, and Pasha. Sorry, Pasha, right. So we are a Tech Internals community, organize events for the developers of highly loaded and complex systems at scale. So please scan the QR code to explore our main event that is going to be in May here in Berlin on a beautiful venue, and you can just follow the QR to understand more about the conference itself. But really quick in numbers, we have already hosted over 100 events for the developers, and now we decided to bring this product, this conference from developers for developers to this huge IT hub like Berlin, right? And this is the key topics of our meetups as well as of our conference itself. So it's architecture, DevOps, software engineering, and others you can see on this slide. But basically, we are all about really in-depth tech talks. So if you can take a look into my hoodie, skip this small talk, let's get technical. It's all about us. We are not about time management, marketing things, and something like that. We are all about practical tech talks.
Can you go back to the QR code?
Sure, yep. Please scan it. Okay. And this is some top talks of our previous conferences. You can see some really interesting topics in here, as well as people from well-known companies, including Amazon Web Services, Dropbox, Mira, and others. For the next conference, we'll have guys from Red Hat, Amazon Web Services as well as Netflix. So like the agenda and the lineup is really cool. This is some information about attendees of the conference, so you can understand what community looks like. But basically, one important thing you should understand is that because of the level of the talks, we mostly attract middle-class specialists. So our conference is mostly for middle-class specialists. And this is some pictures from our previous conferences, including the main values of it. Of course, the main value is our program, so top speakers and cutting-edge topics, as well as community. We are building the community. And also, of course, some entertainment and after-party. Guys will have some beer during our meetup and at our conference as well. And before I'll pass it to our wonderful speakers, I would kindly ask you to scan the QR code. It will take you only 2 minutes to go through the really quick participant survey. There is nothing like super special about it, so let's take 2 minutes to do it. Okay, if somebody wasn't able to scan it at the moment, we will have it at the end as well. But yes, so thanks a lot for your attention, and now I would pass it to Jérôme, our first speaker.
Hi everyone, so I'm Jérôme, and I'm here today to talk about the worst container image I've ever built. And maybe I should start by giving a little bit of context, because you might be thinking maybe this guy just learned Docker yesterday and he wrote one hello world image, and so there's going to be nothing too surprising. Actually, I have more than 12 years of Docker experience, and now you might be thinking, okay, this guy is telling us bullshit because Docker is not 12 years old. But actually, I worked at Docker. I started there in 2011, so before it was Docker. And so I had the joy of using Docker before it was out in the world. So you can imagine I saw many pretty horrible Docker images, and this is going to be my worst. But as often, there is the nice hello world, which is like very like best practices and everything, beautiful. And then there is the actual stuff we have in production, and actually that image is a production image. I'm going to explain where and how and why. So yeah, in the past I worked 7 years at Docker. Now I'm a Kubernetes teacher and pirate because last year at KubeCon I gave a talk about database operators and I dressed up as a pirate. That was fun. And when I'm not working on containers, I'm doing music and tinkering with Raspberry Pis and MIDI controllers and stuff like that. All right, so first I'm going to explain like what that image is, why that image is actually important to me at least, and the how, so how it looks like and why it's awful, and maybe there are a couple of useful tips and tricks for you in there as well. We're going to talk about cross-compilation and emulation in the context of building images. We're going to see clashes between musl and glibc, and I'm going to try to wrap up with takeaways at the end. So first, what is that image? It's something that I called shpod, like shell in a pod. The source and everything is on GitHub, and basically what it does is that it lets you have a shell in a container like this, like you docker run jpetazzo/pod, and it's a container image with about 30, 40 container tools. So there is, the Docker CLI, Compose, kubectl, Stern, Helm, etc., etc. And so if you run it with the terminal, you get a shell. If you run it as a background container with -d, then you get an SSH server. Now you might wonder, why is it called shpod if it runs in a container like in Docker? Docker doesn't run pods, because you can also run it in Kubernetes, and actually that's the way I typically run it. And so just to have a really quick demo of that, actually let me quit that so we don't have that little thing. All right, this is an example. I'm going to docker run -e password equal hello because security matters. Expose 2 ports like this. There we go. And now I can SSH -p 10, or actually I can even simpler, docker exec in that thing, took. And once I'm here, whoops, nope, sorry. There we go. So once I'm here, that's all the stuff that's available in there. Yeah, your Helm file and JID and kubecolor, etc., etc. It's kind of like my Swiss Army knife of container tools when I need to intervene somewhere on a cluster and I don't necessarily have everything, my laptop or whatever. I can just run that image and have a nice environment. Now, if I do docker ps here, it doesn't feel really useful because it can't access the Docker socket. So there is this super old trick which you maybe know about, which is to bind mount the Docker socket, the -v. Can we actually, no, sorry, we can't see it because it's too low. All right, -v, which means take the Docker socket on the machine and bind mount it in the container. And so now if I do that and I run this again, if I do docker ps, that works because my container has access to the machine, and we do the equivalent in Kubernetes, basically using the pods service account. Okay, so that's the general idea. So what's what's the point of this? Why do I want an image with all these tools? Because I'm a Kubernetes teacher. I do training. Okay, that was a long time ago, before the pandemic, back when I was still doing tons of conferences. Now my training sessions look more like this, like from home. And what I do is that I give each student a Kubernetes cluster, so that the first thing we do when the training starts is that instead of installing Kubernetes, which sometimes takes a while, the first thing we do is we SSH, we connect to the to an environment, and we have everything that's already set up, and we have completion and color and blah 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 blah. So that's why I need that image with all these tools in them. Okay, so right, that's the general idea. I'm not going to give much more details about like how I use the image and so on, because today I want to talk about more like how it's built. But just in case, if you're interested, in barely 2 weeks, February 10th, we're going to have another meetup about development environments. And so I'm going to talk about more about like how I use that image and what we do with it and so on. And there's going to be a talk by Sergey Petunin from JetBrains about like cloud development environments. All right. That being said, now let's look at the image itself, or rather its Docker file. So I have a bunch of links that I opened here. Yeah, okay. So that's the GitHub repo. No, that's today. I wanted to show some history. Yep, nope. Where is the... yeah, I have opened a bunch of links because when you have a presentation like this and you click on links, it kind of like breaks the flow. But this is also confusing. Yeah, 6 years ago, that's what I wanted to show. The original version of this back in 2019. So very simple, kind of, well, very simple. It's still like 60 lines, but comparatively simple. We just have like, I don't know, maybe a dozen of tools, really like the basics. There is kubectl, I think there is Helm and Customize, completion, you know, really like the bare minimum. It's single stage, it's only for Intel AMD machines, and that helped me a lot back then. That was great. Then in 2020, you know, I doubled the number of tools in the image. That's going to be the next tab here. Yeah, awesome. So, you know, it's probably more, yeah, it's a little bit bigger, but still the same idea. You can see that image is just doing a bunch of like run, install a bunch of things, like, you know, load more and more things in the image. Then in 2021, I decided to change my approach a little bit in two ways. First, I'm using a multi-stage build, and I also decided to support multiple architectures. So we have some kind of weird stuff like here, like a from -- platform. Out of curiosity, has anyone ever used from -- platform? Okay, just a couple of people. So this is typically when you want to do cross-compilation. And I'm going to talk more about that in a few minutes, but it's basically, I want to build an image for ARM, like for instance, a Raspberry Pi or a Mac with an Apple CPU from my Intel AMD machine. And it's multi-stage. You can see that with the from, and so on, and so on, and so on. Each time you have a from, that means we start a new stage. And typically the way we use multi-stage in Docker files is that you have a build stage, like you compile some stuff, and then you have a run stage where you don't have the compiler, you don't have the source, you just have the result of the build. Maybe it's a binary, maybe it's a jar file, and you run that binary or run that jar file with the JVM. And sometimes you might have like 3-4 stages, like, oh, maybe I have a special stage to you know, kind of transpile TypeScript into JavaScript and maybe optimize my images or whatever. But here we are talking about, I don't know, 15 or something like that stages. And the idea is that instead of kind of in a linear way, you know, instead of downloading everything kind of one by one, we download or we build all the tools, each in its own stage. And then in the final stage, we put everything together. These are like this, I don't know, 15 copy lines that you see here that are kind of putting everything together. All right. So if you look at the number of stages, yeah, we went from I don't know, 1 to 20 something, so that's a lot. So we still have a bunch of tools that are installed in a single stage, like everything that was already in packages. I just installed them like this because it was simpler, obviously. We have some tools that I also installed kind of the normal way in the final stage. This is Crew with a K, that's the kubectl package manager, very useful in the Kubernetes ecosystem. And then we have all these individual stages for individual tools. For instance, this is compiling a Go tool called JID. I think this is maybe something to visualize JSON. I don't even remember exactly what that one does. So why am I building it? Sometimes I build it because there is just no binary available. It's just like provide the source. And sometimes they might provide a binary, but only for Intel AMD 64. And I want my image to also work on other platforms. So then I just decided, let's build for everything. And sometimes we also just like download an existing build. Some folks ask me, why do you download in a separate stage? You know, downloading should be pretty fast, so why do you want to separate that? What's the point? This is because all these stages happen in parallel. So all the builds, all the downloads, everything happens in parallel, which makes the whole build like much faster. So the whole thing, you know, like the current version, which has, I don't know, more than 30 stages and 40 tools, you could think, oh, this is going to take like, I don't know, 20 minutes. No, this is the build time, and it's not even using a cache. I thought I would need to add a cache because I was scared of like, okay, the build time is just going to kill me. But no, actually, this is on a normal, like the free GitHub Actions, not even bringing my own custom fancy runners or anything. And this is building for 3 architectures, 2 of them using emulation. And it's 4 minutes without cache. So that was perfectly fine with me. Maybe when this goes past 5 minutes, I'm going to try to add cache, but for now that didn't feel necessary. So the whole point also of this approach, you know, build in separate stages and bring everything together, was to avoid, you know, bring extra crap in the final image, to have a small image. Well, small image is kind of a relative concept because currently that image is 2.2 gigabytes. And believe it or not, but that's actually fairly optimized. And I see kind of doubt on your faces. But I'm going to explain why it's so big in just a few minutes. All right, so one little detail. So for a while, the Docker file was, you know, when I was starting to do the not just the multi-stage, but the multi-architecture part, it was really ugly, and I didn't like it because you had to download the releases for each different platform. And the problem is that on some programs, when they publish releases, they use the Go convention, where Intel AMD 64 is AMD 64. And sometimes they use the GCC convention, where it's x86-64, which is also what you see when you do a name, uname. That's the little string here. So it's 2 different conventions. And so, you know, if you think about, I'm going to just download some tarball from GitHub or whatever, often it's going to look something like this. You know, you have to put like, sorry, that's probably a little bit small, but you have to put crew Linux $target arch, and this variable is going to be either AMD 64 or ARM 64, depending on what you compile to. And so the fact, you know, if everybody had agreed on a single standard, like it's going to be AMD 64 and ARM 64 and maybe ARM 32/7L or something for 32-bit ARM, you know, if we had a single convention, that would be great. But I think I missed an opportunity here to use, you know, the XKCD comic about, hey, we have 13 competing standards. I know what we need to do. And that's how we have 14 competing standards. It's not that bad. You know, we don't have like 13 different ways to represent architectures. Basically, we have 2 main ways. We have the Go arch way, so that's the way that Go uses. We have uarch. I mean, I call that uarch because it's what you see when you do a uname -m. And then there is what I call the WTF arch. Some programs decided to publish their releases where the Intel AMD one is x86-64, and the ARM one is ARM64 instead of ARch64. So it might not seem weird to you like this, but it's a little bit as if I were publishing some documentation, and the documentation for my program on Windows, it's in French, and on Mac, it's in Italian, because reasons. The solution to this, it's the kind of stuff where you're like, okay, I'm just going to put a million of like Ks in my Docker file, and at the same time you're like, no, I'm way too lazy to just have like 30 or 35 Ks sections in my Docker file. So I ended up having a little helper, which, as you can see, it's going to do a kind of a search and replace in the URLs. So in the Docker file, what I end up doing, where are we? It's going to be, no, that was to show, yeah, this one is an offender where you have, oh no, actually it looks like they fixed it now. Now it's MD64, M64. Great, awesome. Yeah, now I can update the Docker file. But not so long ago, they were still using x64. Great, so I'll be able to simplify things a little bit. Okay, that's going to be a more recent version, and you can see what the code looks like. Basically, here, I have this helper, and basically there are kind of two strategies. Sometimes you directly have the binary, and so I just download the binary, put it in the right place. So that's what you see with helper bin, helper curl. There we go. So helper curl bin, that means download the binary, and so the helper just like puts the binary in the right place. And sometimes you have a tarball, so you want to unpack the tarball, and almost, I would say like 99% of the time, the binary is not directly in the tarball, but in the subdirectory, so you want to extract that. So I just did a little helper so that in the Docker file, I don't have to repeat like 1 million times the same thing. It's just like, a bunch of URLs, and that's it.
Does it remove delete the leftovers?
Yes. Yes and no. What I try to do is to extract just a part I need. So the question was, do I delete the leftovers? Because one of the classic kind of traps when you install from a tarball in a Docker file is that you get the tarball, you unpack it, and actually you only want one file, so you're going to take that file, copy or move it to USR local bin, and be like, okay, done. And if you do that, then you still have the tarball and a bunch of files that you don't want. So idea number one is you run rm-rf all the crap I don't want. Unfortunately, that doesn't work. I mean, it works in the sense that the crap disappears, but it's still in the layers of the image. It's a little bit like if you have a Git repo and I accidentally add some, oh, I just added my cloud credentials in the repo, and I commit and I push, and I'm like, oops, git rm, git commit, git push, too late. The credentials are in the history of the repo. So not only they've leaked, but if somebody pulls the repo, the credentials are going to be here. So same thing with the Docker image. If you have a stage that downloads and uncompresses a tarball or zip file, it's kind of too late. It's going to be in the layers of the image. Unless in your run command, you kind of string everything together. So you put a single command that like curls plus star plus move plus rm in a single operation. Or you can use multi-stage, because with multi-stage, it's fine. In your build stage, you can put all the crap you want, because at the end, we're just going to take the one file or the few files that we care about. So in that case, in the helper, if I can show you what it looks like, I try to do things in a kind of like, look at me being fancy and kind of like curl, pipe, tar, etc. So that, I try to not have too many temporary files, but it doesn't matter because we're in multi-stage anyway. So at the end, I just get the binary. So it's okay if we have some extra stuff anyway. Okay, so all right. Now we get to the multi-arch file part. Sorry. And here we have a few different strategies. So basically, this is going to be about cross-compilation versus emulated compilation. First, we have a little bit of kind of Dockerfile magic in the beginning, the from -- platform. So what's that about? Normally, when you build a Dockerfile, it just builds for your machine. So if you have a PC, usually it's going to be a Intel AMD. If you have a modern Mac with an Apple M something CPU, it's going to be ARM, and so on and so on. There are not like that many arches available, but these are the two main ones that we are dealing with today. Now, if I want to make an image that will work for both, the way it works is that I actually build two images, and then there is something called a manifest list v2 thing, or informally like a fat manifest, which is a kind of, it's like an image that just links to two other images. It says, and so when you try to pull it, the registry is like, this is actually not an image, this is actually a pointer to, there is an Intel image and an ARM 64-bits image and an ARM 32-bits image and maybe a Windows image and maybe a whatever image, and then your local Docker or Kubernetes, whatever container engine is going to select the right one and run it. So here, the -- platform means I actually want to use a different architecture, and I want to use $build platform. And $build platform, it's a kind of special variable that Docker is going to set to the local platform. That means even if I'm, so this is a PC, so with AMD whatever CPU, if I try to build for ARM 64, so there is a target platform which is going to be Linux ARM 64, but build platform is going to be Linux AMD 64. So it means that these commands here are going to run with my local architecture. So if it is the PC, it's going to run like PC stuff. Why? Because this is going to be my builder. Oh, even nice highlights that I should have used when I was explaining all that. And so in some languages, we're going to have amazing support for cross-compilation. For instance, in Go, all you have to do is set a couple of environment variables, Go OS and Go Arch, and then Go is going to cross-compile. Which might not seem like much. It's like, yeah, okay, I'm just setting these variables. What's the magic about that? Well, 20 years ago or something like that, I was trying to build some ARM stuff on an Intel machine, and I spent, I think, 2 weeks of my summer vacation as a student trying to get it to work before like table flipping the whole thing and deciding that it was not worth it. So we really improved the situation a lot. I mean, even for C code today, it's way easier. But the fact that for Go, all you have to do is literally these two variables and Go build, that's really great. So I don't actually compile a lot of things in that Docker file. There is that JID example here. But so when I do it, I run it with the native like local architecture. Like my AMD CPU is going to generate binaries for AMD, Intel, ARM 64 and ARM 32 bits. Now, sometimes you don't have a cross-compiler, and by that I don't mean it's impossible. I mean sometimes you're actually too lazy or incompetent or whatever, or you're really unlucky and you can't get the cross-compiler to work, and after pulling at your hair for a while, you end up like, okay, I'm just going to fall back on emulation. So emulation, that means that you're going to run the like normal compiler, like the ARM compiler, but you're going to run it on your Intel AMD CPU. So there is emulation going on here. It's a little bit like a virtual machine, but not quite, because in a virtual machine, the boundary is that the virtual machine has like a fake network interface and a fake disk controller and a fake everything, and you just run a whole system in that. And here we're using something called QEMU user, and in QEMU user, the boundary is actually Linux system calls. So you have ARM code that runs on your Intel CPU. So you have some binary translation thing going on here, like actual CPU emulation. And each time the code tries to talk to the system, like open a file, open a network socket, move the breakpoint to allocate some memory or whatever, then this is translated to a normal syscall on your normal machine. So the nice thing is that lets you kind of magically run, let's say, an ARM program on your Intel machine on Linux as if it were a normal binary. You don't even notice anything. You're like ls, and you don't know that ls was actually a binary for a different architecture. First time I saw that, I was like, this is magic, and after a while, the novelty kind of wears off. But the way it works, so it's a combination of binfmt or maybe binfmt, and so that QEMU user thing. The really nice thing is that setting that up, you might think, oh, that seems to be really like nifty and complicated. Actually, there is a one-liner. You can do a Docker run -- privileged because it's going to kind of hook things in the kernel. A one-liner that runs an image and that's going to register all that emulation stuff in your kernel. So then that lets me build that one program here, HTTPing, just because in my classes at some point we're like, we have some latency on that microservice. Let's measure that with HTTPing, which is just sending HTTP GET request and showing you the latency. And at some point when I started, that whole project like Spod, container, and so on, I realized, HTTPing is available on, I think it was on it was kind of embarrassing. I was using HTTPing, a binary that I had found somewhere in a corner, and for years I had been using that very sketchy binary. So okay, that can't continue. I need to find the source and build it correctly. Then I realized there was I don't know if it's a bug, but basically when I was doing it on Alpine, I would do a ping and it would give me negative ping times. So I was like, that seems really sketchy. And I found something like, that's what the weird set-i here. This is to avoid the negative ping time. This is a fix I did like 5 years ago, so I don't remember the exact reason, but I think it might be related to time zones. Anyway, that works, and what's even better is that it works on all architectures because the code of HTTPing is really simple, so there is nothing, well, except for that weird stuff, there is nothing too weird happening. Okay, so, then that little Docker file keeps growing, 2023, we had like 270 lines, 2024, 300 lines, almost 30 stages, great. And at that point, you're like, I'm feeling really happy with the result of my work until 2025. So in the very early days when I was starting to teach Docker and Kubernetes, so when I quit Docker in end of 2017, early 2018, I had a really bad depression and burnout, and I was like, okay, I need to take a really long break, at least 6 months. And after taking some time for myself, I realized, okay, I can still work in tech, which is great because I was already thinking about, maybe I need to recycle my career and I don't know, craft artisan baby goat cheese or something like that, which would be a shame because I would probably be very bad at it. But after a while, I realized, okay, I'm still fine working with computers. And actually, I absolutely love teaching and sharing the weird stuff I learned about, which is why I'm here today. And so in the beginning, honestly, most of the folks I had in my classes were, super excited, overhyped about Docker and Kubernetes, and they were super deep in the terminal and everything. Well, except that one time when I was telling, okay, now we SSH on the server, and that gentleman asked me, where is the SSH option in terminal server client? But other than that, most oftentimes, folks were, kind of technical. And over time, there was a shift. I still have a lot of really technical students who are, already have a lab with Raspberry Pis and Kubernetes at home, but I also have folks who are learning this as it's just one of the many technologies I have to learn to do my work. And more folks were kind of telling me, okay, you are editing files on the remote machines with VI or whatever, but we don't like it that much. It would be nice if you could offer us something better. And for a while, you know, I knew we had options like some VS Code you can run in the browser. I mean, not exactly run in the browser, but you run that backend somewhere and then you connect to it in the browser. And eventually I decided to add that to my image. And that's where it gets absolutely ugly because that's, okay, so code server, first to clarify, code server itself is not ugly. I want to make it very clear. I'm in no position to cast a judgment on the code. No, the part where it gets ugly is because, well, my whole thing so far was based on Alpine, I don't know exactly what's the official pronunciation, Alpine, yeah, which is using musl or musl, which is a different system library from every other Linux system. And code server provides pre-built packages for glibc. So we have a library incompatibility here, and I had dealt with that in the past, and I knew that would be a bumpy ride. So, okay, what could we do? Well, we could rebuild code server for Alpine, okay, or Alpine has some nice compatibility layers to run glibc programs, or we could try to mix musl and glibc, or if it doesn't mix well, we could forcibly mix it, or we could just like switch away from Alpine. Well, let's see what happens with all these options. First, code server, it's in Node.js. So my first reaction was, well, I don't need to build anything. Node is an interpreted language. I mean, Node is an interpreter for JavaScript, I guess. So there shouldn't be anything to compile, and it should just work fine in Alpine. Except in Node, just like in Python, Ruby, and pretty much every interpreted language, well, maybe not every, but most interpreted languages, you have native extensions. And so when you npm install or pip install or gem install or etc., sometimes it needs to build a little bit of code, and that's where things get bad. So that's why the pre-built version of code server doesn't actually work on Alpine. So, right, okay, let's build it. You have to install a bunch of packages and you know, do some sketchy npm install -- unsafe perm, but it works on AMD64. It doesn't work on ARM64, at least not in emulation. Maybe if I run it on a real ARM64 machine, it would work, but I didn't even want to try because my build server, my build process would be using emulation anyway. So I don't know. One thing I forgot to mention earlier about the emulation thing is that it's not completely perfect. Sometimes there's going to be, I don't know if it's a weird syscall or whatever, but sometimes you just get like a random seg fault, and that sucks. So in that case, building code server for ARM64 on my AMD CPU didn't work. Like, okay, there goes nothing. Let's try the compatibility layer. So you just apk add gcompat, so that's really simple. And like most simple things in life, it actually doesn't work. Big disappointment. So there were like, at first, lots of missing symbols, you add some missing libraries, you try again, full of hope, and then there is just like one missing symbol, FCNTL64, and you're like, oh, that's probably easy to find. You start to look around, and you realize, nope, that's missing from gcompat. So there is like one function that they didn't add. So I tried a bunch of things. What if I build my own version of gcompat with one extra function? What if I try something with LD preload? But that all felt very brittle, and I didn't want to go there. So like, okay, let's try something else. Can we mix musl and glibc together on the same system? And at first, it seemed like an impossible proposition. And yet, with NixOS, you can do it. Out of curiosity, who knows about Nix and NixOS? A few hands. Nix is kind of like, I don't know, I guess it looks like when all you have is a steam engine and suddenly somebody shows up with a fusion reactor and you're like, what's going on here? So in Nix, you can do something like this, where you install side-by-side things using completely different and even incompatible libraries, because each program is going to use potentially a different linker and a different set of libraries. So it's kind of magical, where you could have a library with two different versions, incompatible, and they could still be both installed side by side, and some programs would use one, some would use another, and that works. So full of hope, I gave it a try, and yep, it works on AMD64 and ARM64. AMD and ARM64, like the main two targets, but it doesn't work on ARM 32-bits, like old Raspberry Pis, because we don't have NixOS images for ARM32 on the Docker Hub. So I was thinking, well, Nix does support ARM 32-bits. It's just that whomever is maintaining these images thought it was not worth the trouble of pushing them to Docker Hub. So I could probably build my ARM 32-bit images, but nah, I was like, this is too much work and too much maintenance, so let's try something else. Now, what if we do something like this? There is a program called LDD, which you can run on whatever, you can run LDD on a binary, and it's going to show you the libraries used by that program. So for instance, if I do, where is it? Code server, LDD, user local bin code server. This is like actually, that might be a script. Yeah, I think the real thing is probably somewhere here. Yeah, okay. So that one is using a bunch of libraries, so basically what this absolutely ugly hack is doing is find out which library files we need and just copy them in the final image. Do not do this, do not recommend. Here lies madness and bad things. So it still worked on Intel, but it didn't work on ARM64, probably also because of emulation. So again, okay, didn't want to try it on the real thing because I don't regularly have access to a real ARM64 machine, and it would be, for the build process, it would be complicated. So next solution.
But GitHub has an access to ARM64 machines.
Oh, I did, so apparently GitHub has access to ARM64, so maybe I could find a way to set up GitHub Actions so that it runs on the native thing. I'll definitely give that a try because that could simplify things a bit. But so what I thought was like, hey, what if instead of trying to find out precisely which library files we need, what if we just get all the libraries, for instance, from the Node.js Docker Hub image, so because that's going to be all the libraries we need to run Node programs. And surprisingly, that worked extremely well on the first try. It feels a little bit janky because as you can see, the name of the linker file is very different from one platform to another. And then the path where the libraries are is also different. But if I want to add support for one architecture, all I have to do is add like one word here, one word there, and that works. So this is the current situation. And in theory, that could cause problems. In theory, mixing like this, the two libraries on the system, I don't know, like maybe this is actually going to cause a rip in the fabric of space-time and we're all gonna disappear in a parallel universe. Probably not though. And so that's what I have in the image at the moment. And that's why that image is, as I was showing you, 2.2 gigabytes. If we take the normal image, it's only between quotes 1.6, which is still a lot. But we have 600 megs just because we added code server. So now what that means is that we can do something like this. There we go. And basically, so This is going to look like Visual Studio, except it's actually code server, and this is in my browser, right? Let's see if I can move things, zoom a little bit, and so yeah, I can do stuff and edit files, and also we have the Docker and Kubernetes extensions, so we can actually see the containers that are running here, and so on and so on. I don't use VS Code on a daily basis, so I can't give you a tour of all the wonderful things that are in there, but apparently people really like it, and a bunch of students were like, this is really nice. So I was like, okay, I didn't sweat that much and write all these horrible things for nothing. So the reasonable thing in the long run is probably to switch to a glibc distro. Forget about Alpine, because in the beginning I was using Alpine to have a really small image, and also because installing packages on Alpine is super fast. So if you're in the middle of the class and you're like, hey, I need, I don't know what extra package, you do apk add, and it's really ridiculously fast. Well, we already have curl here, but just to show you what I'm talking about, in case you haven't used Alpine, there we go. We just installed curl in like, I don't know, 2 seconds, and that on some local, probably not super fast guest Wi-Fi. Okay. So I don't know if I want to give up on that convenience because it feels so nice to install things so fast, but probably that's the reasonable option. So to wrap up, there are a few hidden reasons, like stuff that wasn't really in the spec in the beginning. You might think, oh, you could probably improve this further, and I kind of gave a bunch of ideas of how this could be better. Now, this thing is just a tiny part of what I call my training stack. Of course, I have training materials, like more than 3,000 slides, which I maintain, like update all the time. I have a bunch of code samples, CML manifest, and so on. I also, I told you that since the beginning of the pandemic, most of my classes are online, and I didn't want to teach on Zoom because honestly, it's crap. The video quality is crap, the recording is crap, the chat is crap, everything is crap. At the same time, I was seeing folks doing live streams, like technical live stream on Twitch, and I was like, this is awesome. Great video quality, the sound is great, the chat is great, like everything is great. That's what I want. So I ended up kind of cobbling together my kind of own local small-scale Twitch. And that's what I use to teach, but that's a whole stack, with video transcoding and streaming and so on and so on. Plus, I have all the stuff to deploy the Kubernetes clusters on more than 10 different cloud providers, just because sometimes a customer is going to be like, we're using Hetzner or DigitalOcean or GCP. Can you show us Kubernetes on that? And then I'm like, oh, yes, of course, Terraform. So that's a lot of things to maintain, and that image is just a tiny little piece of all that. So I want the maintenance to be as easy as possible. Ideally, I want that stuff to just exist there. The only maintenance I do actually is that once in a while I'm going to bump up the versions in the Docker file. You might have seen there was a bunch of like build args, and so sometimes I just go there and I check what I want to bump. And so far, I'm going to, that's not really good wood, but knocking on wood, so far, I never had to do a big refactor because something broke in an unexpected way. With that code server stuff, though, I don't know. And just to be clear, it's not the fault of code server. It's just because I kind of just like increased the complexity of the whole thing a lot by bringing in a whole like big node app along with the node interpreter with the different library and so on and so on. So I'd like to, let's see, let's check again in 5 years. For 5 years, like that image was great. Now, let's check again in 5 years and see if I ended up having to rewrite everything or if it kind of kept working. Also, some folks ask me, why do you want to still support, like ARM CPUs and things like that? Everybody is using Intel AMD. Well, no. First, anybody seen that movie? Almost no one, so that's hackers, yeah, right? And risk architecture is gonna change everything. Well, a little bit different. It's more like ARM that we see, but ARM is RISC. And there is also that provider, they're French, and I'm sorry because earlier I lied. I said that the screen worked great, but actually this is truncated because the aspect ratio of my screen doesn't match exactly the aspect ratio of the projector. But on the lower part, it says designed and assembled in Paris. So these folks actually sell you like bare metal RISC machines, and they are pretty cheap. And so I also want my stuff to work on that eventually because why not? And most usually I wanted to work on ARM because ARM often ends up being way cheaper than Intel AMD when you run it in the cloud. It kind of depends, you know, but because it's just like so much more power efficient and electricity is kind of one of the big driving costs in hosting. If you have a CPU that can do the same thing with less electricity, it's going to cost less. So I really want to keep multi-arch support. So there are many things that I could do in the future. And by the way, I forgot to mention, but there are also official images for code server. So I could use that, except the official code server image doesn't have all my tools in it. So I could very easily have code server in a container. But then when you pop up the shell, you don't have kubectl, Helm, and et cetera, et cetera, et cetera. So that would be kind of counterproductive. So conclusions is that once you kind of know how to do it, and once you have honestly, I think one of the biggest thing in that was the helper curl thing. Once I had written that little helper, writing the multi-arch stuff felt really, I don't know if I would say easy, but not awful. Mixing glibc and musl is possible, but I don't recommend it. Another thing, well, Leonela gave us a little speech at the beginning, but there is this conference, TIC Internal, which is happening in May. And if you like, you know, deep dives and highly technical stuff, even more technical than this talk, can you believe it? Joke aside, no, check out that conf because that's my kind of content. I think I kind of like to do the splits between either the really deeply technical talks or the talks about sustainability, mental health, how do we not burn ourselves out, because that happened to me. So I was already interested by the topic before I burned out. But anyway, and finally, I also do a tiny little bit of self-promotion for myself. If you would like me to train your team on Docker and Kubernetes, just check on LinkedIn. And ping me, I'll be happy to set that up. And that's it, a bunch of useful links. I think I mentioned we're going to have another meetup in 2 weeks, right? Where I'm gonna talk again about that image, but this time not how it's built, but what I actually do with it and what it looks like in a teaching, learning environment, as well as for a day-to-day Kubernetes development environment. And I think, yep, that's it. I had put my phone as a clock here, but it's kind of upside down, and so I had a hard time like speaking at the same time checking the clock, so I have no idea how we're doing on time.
We're actually doing almost on time, so I think we still have time for Q&A.
Okay.
Yeah. So please, guys, any questions?
Do you have questions? Yes.
Why couldn't you derive from code server and then install all the tools there?
Excellent questions. Why couldn't I derive from code server and add my stuff in it? So I considered that, like the idea, so one part is easy. The part of like taking all the binaries and kind of shoving them in code server, that's really easy. But then there is a little bit of finish, so to speak, like in the home dir for the user in the image, I set up a bashrc, bash profile, all these little things. And honestly, I think if I wanted to go all in on code server, that would probably be doable. But one of the hidden requirements that I forgot to mention is that I really wanted to be able to keep building both images without kind of copy pasting the whole Docker file. And here, I didn't even show that, but there is a little trick at the end of the Docker file. Let me show you. So the same Docker file actually builds two images. Ooh, scroll, scroll, scroll. So it builds what I call the basic spod image, and it builds the vspod image, so VS in a pod, and it works like this. Like this is the part that builds spod. So yeah, there is a from where is it? Scroll, scroll, scroll. Yeah, from Alpine as spod. So that's the final image. And once I have built that image, suddenly we start a new stage. So that's one stage for the Node.js libraries. That's the stage where you put together code server. And then at the end, I do again from spod. Like what? The thing is that when you do a multi-stage build,
you do it another way.
Yeah, by default, it's going to build the last thing in the Docker file. But you can also use -- target to say, no, instead of the last thing in the Docker file, I want you to build that particular thing. And so if you build that Docker file, just like Docker build, it's going to give you the last stage, so the basic spod without vspod, without code server. But if you do Docker build -- target vspod, then it's going to give you the one with code server added to it. So that was another, one of these kind of hidden requirements. And again, to be transparent with you, so I put that together just a few weeks ago, the code server part. And this week, I'm actually teaching my first class using it. Last week was Docker, this week is Kubernetes, and so far the folks like it. I mean, not everyone, because many folks are just using SSH and they don't care about that, but some folks were like, this is cool. And so far it looks like it didn't break anything else, so maybe I'll just put that in the image by default. But a part of me would still like to have a more lightweight image somehow. That would be nice, so that sometimes when you know that your network is not super fast, you can still use the basic image that has all the tools but not code server.
I would be user of spot, not VS Code.
Yeah, me too.
VS Code is also.
Yeah. But I want to be inclusive.
Yeah, versatile, easy.
Other questions? Yeah, sure. Thank you.
I think I have a solution for you. I mean,
so I have a feeling that I had to be a first speaker because Jérôme gave you so much advanced stuff that my presentation will actually be very, very simple. But I have a promise for you. So he said, was it like the worst image you ever built? The name was, yeah. So you will see the actually bad image in this presentation because his image is just big. This will be ugly. And this is my promise. And you will learn that you shouldn't do a thing like that. You probably know my name, and yeah, I work as a developer advocate at BellSoft. And if you sit too far away from me, this is how I should look. Do not look here, look at that guy. He is beautiful, I'm not. I work a lot of time with JVM, different languages. Who is familiar with JVM here? Some of you. Okay, that's good. So I do not need to dive into what is Spring. Who knows what is Spring? For those roughly 10 people who do not know, Spring Framework is the main framework in the Java ecosystem. It's like 80% of enterprise Java market, and probably Kotlin market too. Yeah, you can find me on Twitter, on Blue Sky, wherever, on Mastodon. You will see my credentials almost on every slide in bottom left corner. Just I don't know, if you want to take a photo or whatever. I also should put this slide in here. I work for a company called BellSoft. We have our own JDK. It's called Liberica JDK. It's about liberation and so on. We contribute a lot to OpenJDK. we are the sole contributor of the whole ARM32 support for JDK. So if you run your Java on a very old device or just a very old Raspberry Pi, we are the guys who made it possible. We have our own base image, and actually we have a solution for Jérôme. It's called Alpaquita. It's right here. It's our own Linux. It's a fork of Alpine. We have support for both musl and glibc. Like, we have 2 flavors of this. And since he needs glibc in his image, and he still wants to have APK install, APK8 command, we are the guys who can give it. Yeah, we also are officially recommended by the Spring Framework, but it's the most important point is we know our stuff. We know both our Docker stuff and our Java stuff, just because they are the only thing we do. So you probably saw the name Ultimate, Ultimate in the name of the presentation. What is the Ultimate? Probably there are several approaches to answering this question, and for me it's either smallest image possible, like, I don't know, 5 megabytes is good, 1 megabyte is better. Probably it's the image that starts up faster, because who thinks that Java is slow? One person. Okay, actually a lot of people say that. A lot of people say that. Actually, I saw with my own eyes Java applications that start for like 2 minutes, 5 minutes. The startup is ugly, and sometimes we want to reduce its time. And maybe it's something in between. Maybe it's not too small image and not too fast image, but in some way better than the original one. Let's look at all of them. But let's first look at the most ugly image you can build. You just take an image with JDK. Folks, can you read the code? Yes. Come closer. So we create something from JDK. We copy our whole application to the Docker image. We change the directory to the application and call build, grelw build. Grelw is just a build tool from the Java world. And then we define our entry point. And this is the worst application, the worst Docker image you can actually build. Because if we look into it, well, I won't repeat what Jérôme already said, because all the layers are immutable and so on. Let's just jump to an example. The same example. Let's look at the resulting image structure. I'm using the utility called dive to look inside what's inside our image. There are multiple ways to look inside an image. I like dive because it's very interactive. So first we have 7.5 megabytes of shell or something, then a bunch of descriptors, metadata, and so on. Then we have 98 megabytes of our JDK. Then we have 67 megabytes of our application. Why our application takes 67 megabytes? It's kind of obvious. We built it on our machine before copying it to the Docker container. Then we have 512 megabytes more because we had to download half of internet to build our application. It's Gradle and it's Java, all the jars are big and so on. And then we have our entry point, which is obviously 0 bytes. And it means that the simplest image we can build with Docker, with our Spring image, will take for almost hello world application 580 megabytes. The question is it bad? Well, probably it's not, but I would argue that it is. First of all, push to your Artifactory or whatever you use will take this 579 megabytes every time, which is just a waste of space on your hard drives. What is worse, pull will take more time. And it means that when you deploy such image on your Kubernetes, deploy will be humongously long. Imagine you deploy it on 1,000 nodes, you will have to download roughly 600 gigabytes of data. Well, it's probably a place where you could save some time and some data, some disk space. So let's try to optimize it. We have this simple image, the image as it was, changes to something like this. We built our Java application on our machine, and then we copy the whole jar to the Docker file. We are kind of in better situation here than folks with Go. They have to cross-compile for several architectures. We do not. One jar will work on any architecture. If you do not have some native calls, probably you do not, if your application is usual. Otherwise, well, you already know how to shoot your food, and you probably built for one specific architecture, and that's fine. And then, well, the image actually becomes significantly smaller. It's 67 megabytes, it was 67 megabytes of JDK and then 500 something of dependencies. Now it's just 60 megabytes of our application, which is a lot, but well, 60 megabytes is order of magnitude better than what we had for every pull and push, which is a lot. Well, I mean, we just saved half a gig and we did almost nothing for it. But there is an issue with this approach. This is a dirty approach. We usually do not want to build anything on our machine because build shouldn't be environment dependable. What if we have some environment variable set up which makes the build work one way and do not work another way? And yeah, we would always prefer to have clean builds. And for that, we have build stages. Who understands the concept of build stages? Jérôme knows. Yeah, like so. So multi-stage builds, as Jérôme said, allow us to build a nice pipeline without copying too much data to our final Docker file, to our final image. It allows us to package optimally. Actually, it allows us to use different base images. And this is how we will make the first iteration of improvement of our Spring build. First, we will use JDK as our builder. Then we will copy our application to the builder. And we will actually build it as we did in the first very bad example. Please don't repeat the first very bad example. Please repeat this one. It's significantly better. And we do not really care about the size of builder because we do not use it in production. In production, we use the image called runner. As you can see, here I use jar E instead of JDK as a base image. And difference is jar E doesn't include all the SDK of Java. It only has Java runtime, which is significantly smaller. jar E slim musl actually takes like 27 megabytes or something like that. It's very small. It's almost an order of magnitude smaller than full JDK build. And then we copy our artifact from builder to our application. And I do not put entry point here. Obviously, there should be an entry point on the final layer, which will be something like java-jar, our jar file. And we obviously should expose some ports and so on. But it's not important for our build because build size doesn't change from meta information. And if we look at changes, we will see that 98 megabytes and 58 megabytes are now, well, oh, sorry, yeah, that's essentially all. No, that's not right. Because you can see, give me, where is my pen? Here, you can see that it's JDK. It shouldn't be JDK. So obviously, it's a wrong dive. But it will be just like JDK will be smaller, the application will be smaller too. And at this point, we have an optimal image. Like we actually cannot make it smaller because the only things the image contains is jar E and our jar. At this point, we actually can say we have an ultimate image, but I want to push a little bit more. Let's look at this 59 megabytes of our application. What is it? What does it consist of? Who knows? What's there? What's inside our huge jar file? Okay. There is a concept called layers, and this concept is specific to Spring. The thing is, our application actually consists not only from our code. There are many dependencies. There are many machinery, Spring-specific machinery, like launchers and so on. And Spring knows about it. So let's do the following trick. We'll build our application as it was before. And now we will add one more layer, and we will call it optimizer. And this optimizer will copy jar from our builder. And then it will call this cryptic command called java-jar mode equals tools -jar, our jar file, then extract with layers and launcher. This is, again, a Spring-specific thing. It's not like you cannot implement it for your own application if it's not written in Spring. You can. It's just a lot of code. What it does a magical thing. It puts all the data from our huge jar file in separate directories. Let's look into them, because our runner changes a little bit too. Now we create 4 layers in our runner. First layer is our dependencies of our application. Obviously, dependencies of our application change significantly more rare than our code. Our code essentially changes on every commit. Our dependencies sometimes do not change for months, right? And then we have Spring bootloader, which is just internal Spring machinery. We could put it on the same layer as dependencies, but Spring folks say that we could change loader for you, and you would prefer to have it on a different layer, even if we do not change libraries. Then we put snapshot dependencies. I know, like, most of the people do not use snapshot dependencies in their production. And this is smart choice. But sometimes we just have to, because someone has fixed a bug crucial for us, and they created a snapshot release. They asked us to test it, and now we tested it, and it works. We have to deploy it, because the release will happen in several days or months. I don't know. It strongly depends on the library. And snapshot dependencies tend to update very frequently. They essentially update with the same frequency as folks in these dependencies update their code. And then we have the layer of our application. If we use caching, which we most probably use, Jérôme doesn't use it because his image is being built in 4 minutes. I cannot imagine a big enterprise project in Java which builds in 4 minutes, because it's just because of tests. Java C is relatively fast. It's very fast to compile your code and build jar files. But you will have to run your unit tests, your integration tests, your end-to-end tests, your smoke tests, your load test suite, whatever. It will take a lot of time. So we will use caching. And this is so nice to have all the layers with dependencies and launcher, and maybe even snapshot dependencies, if we have them, pre-cached for us. So we change only one small part. We change only a part with our code. And we also change entry point a little bit. Now we do not use Java --- jar, our jar file. We use jar launcher, which is also a part of Spring Boot. It will be always absolutely the same. Come on. OK, absolutely the same class. Small diversion. These layers I was talking about, there are actually 2 commons. One of them is extract, which we use to create layers on the file system on the optimizer stage. But there is also list layers, which give you like a nice JSON you can handle in some way. For example, you know for sure that you do not update versions of Apache Commons, one library, and you do update versions of another library. for you, it could make sense to analyze with this JSON with JQ, find all the rarely updated dependencies, put them on the one layer, and put more frequently updated dependencies on another layer. So it's just a tool for your convenience. Let's take a quick glance at how it will look inside the whole image. I actually do not remember how oh yeah, I used lazy to look inside my Docker container and find the listing of files in it. So in the root, we obviously see our application. Then in classes, we see all the banners, properties, settings, and so on, which we have, probably database migrations. Then we have all the AOT precompiled stuff. We will talk about it a little bit later. Then I obviously have my code, it happens Monday. We have, again, formal description of what classes do we have and what layers do we have. We have all the meta information. We have SBOM. Who knows what SBOMs are? Actually, I think that it is a topic for a separate talk. SBOMs are essential for building secure applications. SBOM stands for Software Bill of Material, and it describes how our software was built, which components were used to build it, and which libraries were used inside the application. So, for example, you want to ship an application to your government, whatever it is, and they say, are you sure that you're not using Gradle version for build that has this security vulnerability? And you open your jar file, but there is no information about it. It doesn't hold any information about Gradle version or Maven version. It will be inside SBOM. It is crucial to know how your application is built and Spring thinks for you about it. Now then, there are obviously several dependencies, snapshot dependencies, and loader. In total, it's 212 directories and 525 files, which is quite a few. I would probably die writing this code myself to scrupulously dissect my application in small pieces. But Spring does it for us, so actually solve a huge bunch of headache. Now, let's look into what we have here. We have Jerry. We have our layer with dependencies, which takes 57 megabytes. It has jar launcher, Spring Launcher, which is 382.56 kilobytes, 0 bytes of snapshot dependencies, because as any usual person, I do not use snapshot dependencies, but still should have this layer just in case. And my application code, compiled application code, is actually 2.96 megabytes. You can round it up to 3 megabytes, which is nice, because it means that together it's 61 megabyte. But wait, on the previous result, where there was just one jar file, it was 59 megabytes, and now it's bigger. Is it even okay? Pasha, you're talking about ultimate image, right? Image size. But the thing is, we have to remember what are we optimizing for. We do not blindly optimize the image size. We optimize it for something. We optimize it to make our pushes, pulls, and so on faster. And it means, this particular build means that we will have to push and pull only 3 megabytes of data on every commit from our code to our code base, which is like a lot. It's again an order of magnitude better than updating the whole application every time. The thing is, with all this, we just reinvented how build packs work and how BellSoft's build packs work. Who is familiar with build packs? 3, 5 hands. This, I cannot give a huge talk about it, but I can give you a basic concept. Imagine the beautiful world where you do not have a Docker file. And you launch one command, and it builds a perfect application for you from your code, obviously. This command is actually called pack. And here's how it works. We call the command called pack, then build, obviously build my application. My application is called Pet Clinic. Please use this builder. Builder is a nice concept. It's like almost like pre-written stacks of Docker files for us. It's slightly more complicated than that, but what I love about build packs, they isolate us from complexity at all. We do not have to think about how build packs are organized, how they work internally. We do not need to write our own build packs usually, because build packs are already aware of Java, they're aware of Spring, they know how to build a Spring application. We say, where is our application located? And which Java version do we want to use? In my case, it's the latest LTS release of Java 21. And they built the very same, almost the same Docker image. They have a layer with JRE, which is 97 megabytes. They have a layer with application, launcher config, and something else. What was it? Ah, yeah, build process types, again, some metadata. Again, the same level of optimization. We only need to update like 2.5 megabytes. Yeah, something like that. Sizes of my application slightly differ because I performed experiments on slightly different applications. So the idea of build packs, they transform your application's source code into an actual Docker image without you knowing anything about Docker file, without you writing Docker file. It almost like S2I image, which was used in OpenShift, which was popular in OpenShift and popularized by, but it's vendor independent. You can use it on your machine, be it Mac, Windows, Linux, whatever. And yeah, if you look into it, it actually builds better than the default Docker file you would write. Of course, if you already know about layers and you're not lazy, you could do the same. Like, again, in the first part of the presentation, we just reproduced what they did in build packs. It's Spring aware, and it's actually aware of many other images, technologies. If you use Python, they know how to build Python images and so on. Please look into build packs. They might be a bright part of your future. Is this all? Did we build an ultimate image? And you could argue again that yes. And I would probably agree because we optimized pull and push size. But the thing is, optimization is multidimensional. We have to optimize, we might want to optimize not size, but startup time. If we are speaking about popular and fashionable cloud-native applications, it's not about size at all. It's usually about startup time because a cornerstone of cloud-native applications is being able to scale to zero. To be able to scale to zero, you shouldn't be afraid of scaling up. But if startup time of your application is 2 minutes, then scale up to 1,000 nodes from zero will take anywhere between 2 and 2,000 minutes. Almost unpredictable. And are you really ready to force your users to wait for 2 minutes until your application starts up? I think it was a huge issue with Java some time ago. No one liked it because it took a long time to start. And it means it took a long time to scale up. There are several solutions to this problem in Java world. Class data sharing, coordinated restore, a checkpoint, and GraalVM native image. Or we have our own flavor of GraalVM native image called Liberica native image kit. It's almost identical. We have one more garbage collector. That's all. Let's talk about them in order. Class data sharing was introduced in Java 5. I mean, it's technology of ancients. I started my Java experience with Java 5. I'm like, what, I'm 15 years in Java? I don't remember. And the idea was very nice. It was about the reduction of startup time of applications, but the world was significantly different. It was about if you launch several Java applications on the same machine, they could use some of already loaded classes. And this way, in the same virtual machine, you could start up sequential next JVMs faster. And it obviously stored data in some archives. How does it help us? It doesn't, because in the model world of Docker, no one runs JVM on several JVMs on a single virtual machine. It has all kinds of bad side effects, so we need something different. In Java 10, they improved class data sharing, and they allowed us to cache a little bit more data about JVM, but only in Java 13, which is like 5 years ago. Yeah, it should be like 5 years ago. They said that now, when your application completes its execution, we can automatically dump the whole class data information onto your drive. And this helps, because Spring supports application class data sharing out of the box. We only need to add a couple of arguments, archive classes at exit, and path to our archive where we should put them. And also dash spring context d spring context exit equals on refresh, which stands for please spring. As soon as you load all the non-lazy beans, shut down. We do not want to wait for anything else. There are some caveats. First, we have to use the same JDK. It means that if you create an AppCDS archive from your JDK and you want to use it on your JRE, it won't work. Which is a shame, but it is what it is. It's perfectly, but on the other hand, it's totally perfectly possible to create archive on JRE. You actually do not have a reason to create it on JDK, because you do not need anything. You already have a pre-built application for you. You already have a jar file. And you also should use the same arguments. And I mean Java arguments. No one cares about the application arguments. And it becomes even better if you use dash spring AOT enabled equals true, because this way Spring, during the build time, analyzes what is there, what are our beans, what are our classes, how we should interconnect them together, and dumps all this information in Java. And this information is being stored in our application class data archive too. This is how we will build the Docker file, the Docker image with CDS support. I'm obviously skipping two first parts where we split Java jar into layers and so on. Let's look at our from. It changes a little bit. We need to have a JRE with CDS support. BellSoft has it. This is probably the smallest you can find, JRE, CDS, Slim, musl. Then our layers, they remain the same, but now when we build the final image, we have to run a command with all these arguments I was talking about. Spring AOT enabled equals true, archive class set exit to application JSA, Spring context exit on refresh, and then our jar launcher. And our entry point changes a bit too, obviously. Since we just put the application JSA on inside our image, we should add it to our startup arguments. So it will be Java, Spring AOT enabled equals true. Our JSA archive is here, and please use jar launcher to run our application. What does it cost? It costs a lot. I mean, the class archive is 81 megabytes. So essentially lost everything we won on reducing the size of application, reducing the size of layers, reducing size of JDK to JRE. Well, maybe not this. JRE is still significantly smaller than, but it's 81 megabytes for a small application. For bigger application, it could achieve like 100 megabytes. But startup speed is significantly better. It's like folks from Spring say that you can save up to 50–60% of your startup time with using AppCDS, which is not that bad. And it will be better when we release laden support. I probably shouldn't talk about laden right now. But you could probably save up to 75% of your startup time. And cutting 5 minutes to 2.5 minutes is kind of impressive. 2 minutes to 1 minute is probably even more impressive. But we can push further. We can push further with a project called Crack. Here is a huge quote from the Wikipedia, from the Crack site. Crack stands for Coordinated Restore at Checkpoint. An idea is the following. Let's launch our application and then take a snapshot of its memory and save this snapshot to our disk. And then the next time when we need to start up our application, we do not need to initialize Java virtual machine. We don't need to find all the classes. We already know everything because our application is already started. We just read data from disk, restore it to memory, launch from this place. That's all. The results, I will talk about results right here on this slide. You can launch your application in like 50 milliseconds, easy. On better machines, probably 20. On worse machines, probably 100 milliseconds. You will never exceed 1 second. At least I do not know. If your hard drive is very slow and you read for 1 second, then you will exceed 1 second. But, well, it's just amazing. But building an image with Crack is pain in the ass, really. I mean, really. So I will show you the divine magic. You probably won't. You probably will decide to not ever touch it. So first, we don't need our layers anymore. We do not need any layers. We'll lose all. Crack archive will be human goals, and we actually do not need them. But we should say that on optimizer layer that our application should exit on loading non-lazy classes. It should save Crack checkpoint to /checkpoint. It's just a random directory I use here. You can use anything else. And in our runner, we should say something like this. Java Crack restore from /checkpoint. Then please copy from optimizer application. And please copy from the optimizer checkpoint. At least it is how it should be in a perfect world. In reality, this is what you see in this imperfect world. Java lang runtime exception, native checkpoint failed, which stands for, sorry, I couldn't make checkpoint, suck my socks. So we can change Docker file. And this is probably the first time an advanced stuff Jérôme was not talking about, and I'm talking here. We actually have directives in Docker file that allow us to use different kind of syntax, lab syntax. It should ring a bell, like it should be a red flag for you. We are doing something weird here. We use Docker file 1-labs, so it's a preview syntax and so on. Then, this beautiful line, please save checkpoint to /checkpoint, we call run -- security insecure. When your, security inside your company will see this line, they will start asking questions. Are you sure? Why do we need it? And so on. So you should be able to answer them. The answer is checkpointing is a syscall to perform this syscall, you need to have a special capability, and you do not have and do not need it by default. Then, yeah, by the way, this also won't work. This won't work because when you make a checkpoint, application will exit. And it will exit with non-zero exit code. It will exit with zero code 127, if I remember correctly. And when it happens inside Docker build, Docker says, oops, something went wrong, we should stop. And your build has failed. So you can add something like this. Pipe, true, we are sure that it was built correctly. It also raises questions, obviously. I know. But that's not all. Since introduction of Docker BuildX, we can say that we can have different builders for our Docker, almost like build packs. But they're like kind of local on our machine, and we create a new builder, which we call insecure builder. You will have to do it on your CI, and it will raise questions. And your security will ask questions, and you should be somehow able to answer it. That this builder is intended to build insecure images, which sounds honestly bad. Then you can do something like that. Docker BuildX use insecure builder, which stands for I want to build everything with insecure builder, which raises questions. I know. And after that, we say Docker BuildX build allow security insecure -f our Docker file. Well, OK, then it's boring stuff. Because we put insecure word in at least 3 places in our CI pipeline. Someone will be unhappy, but it works somehow. We also can do it like this. It will also, to run this application, we have to call it with privileged, which will also bring questions, because you shouldn't run anything in privileged. In Kubernetes, it's not a trivial task. In general, your privileged containers are by default disabled there, right? Hello. Yeah, but by default? Well, let's say it will raise questions. And then you will see something like this, like 0.2 of a second on my weak machine to launch an application, which took 5 seconds to start up before it. It will be always like this. It will be always very fast. I actually experimented with a lot of different applications. It's very fast. Is it a good solution? If it works, it's enough for you, then yes. You obviously can use it for your pet project, because why not? Your deployments of your pet project will be blazingly fast. If you need some more, please, yeah. Predictable and maintainable thing, you probably want to improve it a little bit. First, you need to build your jar file, let's say in a Docker container, just to have it clear, and then copy it from the Docker container. Then create a new image that will run jar with crack arguments in entry point. Then run the container with capabilities. You need 2 capabilities. Do I have it here? Yes. You need 2 capabilities, cap CSP trace and cap checkpoint restore. It will still raise questions, but significantly less questions. And it's very easy to explain. Checkpoint restore, we need to checkpoint and then restore. ptrace we need just because we need to look into the memory of another process. It's allowed only when you have ptrace capability. It's very, very controllable. Everyone can know what you're doing there. Container will run, and then it will immediately stop. Well, it will take a snapshot, and it will stop. It will formally it will fail. It will run, and it will exit with 127. But it's not important at all, because when it stopped, it saved the crack snapshot on your hard drive inside your image. And now you can call Docker commit container ID and new tag. And this way, you have a perfectly, you should probably also redefine entry point, because we had this entry point that launches snapshot creation. We need to redefine entry point to start up from snapshot. But that's all. There are several good things. It doesn't require any arcane magic. Everyone knows about commit. Everyone knows about system capabilities. It's very easy to explain. We do not need, I don't know, custom syntax support in our Docker file and so on. It works very predictable. You do not need this pipeline true, or pipe true. You can run your tests or whatever. Doesn't depend on unstable features and doesn't require privileged containers to run, which is amazing. When you do not need to run privileged containers, it means that at least in production, everything will be fine. It's okay to kill your CI somehow, but nobody likes to have production killed. Cons, it will be organization specific. I mean, you should define how you build these jar files. Is it a separate CI stage? Is it a separate stage in your Docker file somehow? And it requires more steps, obviously. It's not one jar file, Docker file that solves all your problems. And now, at this point, we have all the flavors of ultimate Docker image. That is, I somehow lost one slide. Native image. I promised to mention it. Native image is amazing. You usually can build your Spring application with native image, but it's long. It will require quite some time for big applications. Can take 20 minutes easily for big applications. And for some applications, it just won't work because they require some external resources, external classes, and so on. And GraalVM native image has its limitations. Let's jump to a quick summary. First, in the usual builds, if you are not pushing for very fast startup time, just please use layers for faster deployments. Or use build packs, because they essentially do the same. If you push for faster startup, I also didn't show you the size of crack snapshot. It's around half a gig, something like that, for a small application. Probably will be bigger for bigger applications, I don't know. Use CDS, up CDS for faster startup times to cut up to 60% of your startup time. For many organizations, that's perfectly fine. And use crack for lightning fast startup applications. Not every C++ application can say that they start up in under a second, actually. You will be better. Thank you so much. Yeah?
I think you can start by optimizing using CDS. So you cut in half.
Yep.
Startup time.
Yep.
You get a raise.
Yep.
Next performance round.
Yep.
Wait for a year. And then you use crack. Then you reduce it for under a second.
Yeah.
You get a second raise.
Yeah, I think it's a beautiful strategy, especially if crack support will become better in this year, which is perfectly possible. Crack has its own limitations. It's not like you can just replace CDS with crack. For example, it's a memory snapshot, right? So if your credentials are in your memory, then you have your credentials saved into a snapshot. It is kind of a risk which you should assess and you should be ready for. Thank you so much. Our QR code again, and yeah, you can find me in all the social networks out there and messengers. Now it's time for your questions. Everyone is bored. I mean, that's fine, yeah.
That's really cool, because I knew some of the stuff because of our past conversations.
Yeah.
But seeing it in action was like really cool. I'm thinking, so a long time ago, I did a really ugly hack that was running QEMU inside a container.
Yeah.
I wonder, would that be useful in that case to get rid of the whole privileged aspect? I wonder if the fact of running the snapshot inside QEMU inside a container, other than the fact that.
Well, wait. It's an interesting question. We didn't experiment with it. It sounds a little bit scary. On the other hand, maybe you're right. Maybe we can do it. Use QEMU static, right? Wait. Yeah, it's already transferable between different architectures, so we will anyways have to build it several times. Probably it's a nice option. Sounds a little bit ugly though, but yeah, it sounds very interesting. What's the overhead of QEMU?
Significant, but
it might be a little bit of an issue. I mean, it's already the build of Java application is already not the fastest in the world, and here we kind of added at 50% overhead to it.
here it could be just for the snapshot phase.
Yeah, but but snapshot phase on the other hand is very fast. How do I? Yeah, well, it's a chat for. It's obviously not a question. It's a very interesting comment. I will experiment for it, and we probably can chat about it the next week, for example.
Awesome.
More questions? Thank you, folks. It was 50 minutes, sorry.
No, that's fine. I think like everyone enjoyed
Yeah, obviously.
of the talks. Thanks a lot, Pasha. Thanks a lot for Jérôme for this beautiful, wonderful. Let's clap again. So, first of all, if you enjoyed our talks today, then you should definitely, first of all, follow our other social medias, including apart from the meetup Conf, in order to keep updated and be aware of this kind of events. And of course, please join our main event. Jérôme is the part of the program committee, so he makes sure that every talks during the conference will be on the same level. So basically, yes, please take your time, right? Also, if you have any questions for me or for our speakers, please approach us during networking part. We are all open. And lately, I've seen that not every one of you participated in the survey, so I would kindly ask you to do it now, if it's possible, of course, and afterwards you will receive some special gift on your email. So please scan it, and that's it for today. So please network, chat, approach to me if you have any questions, approach to our speakers. Thank you. Clap, clap, clap.